Welcome. Today we're diving into exploratory data analysis, or EDA. EDA is a crucial first step in the data science process where we get to know our data before building any models. Think of it as detective work summarizing datasets, searching for patterns, and spotting anything unusual. By using statistical methods and visualizations, EDA helps us make informed decisions for the next steps in our analysis. Let's start by understanding why EDA matters and how it sets the foundation for successful data projects. Main purpose of EDA is to summarize the main characteristics of a dataset, often visually. Before jumping into complex modeling, EDA allows us to understand the data's structure, spot trends, and identify potential problems. This process helps us ask better questions and avoid mistakes later. By exploring the data thoroughly, we can choose the right modeling techniques and avoid being misled by outliers or errors. Summarizing data is the first practical step in EDA. We use descriptive statistics like mean, median, mode, and standard deviation to get a sense of the data's central tendency and spread. These numbers give us a quick overview of what's typical and what's unusual in our dataset. For example, if the average value is much higher than the median, it might mean there are some extreme values pulling the average up. EDA is all about detecting patterns in the data. We look for relationships between variables, trends over time, or clusters of similar values. These patterns can reveal important insights such as seasonal effects or correlations that might influence our modeling choices. By visualizing these patterns, we can better understand the story our data is telling. One of the most valuable aspects of EDA is spotting anomalies, data points that don't fit the expected pattern. These could be errors, outliers, or rare events. Detecting anomalies early helps prevent them from skewing our analysis or leading us to incorrect conclusions. EDA uses both statistical tests and visual tools to highlight these unusual cases. Statistical methods are at the heart of EDA. We use techniques like calculating percentiles, variance, and correlation coefficients to summarize and compare data. These methods help us quantify relationships and differences, making it easier to interpret what we see in the data. With these tools, we can move from raw numbers to meaningful insights. Visualization is a powerful part of EDA. Charts like histograms, box plots, and scatter plots make it easy to see patterns, trends, and anomalies at a glance. Visual tools help us communicate findings clearly and spot issues that might be hidden in tables of numbers. Good visualizations turn complex data into understandable stories. Histograms are one of the most common EDA tools. They show the distribution of a single variable by grouping data into bins. This helps us see where most values fall and whether the data is skewed or has multiple peaks. Histograms are great for quickly understanding the shape of our data and identifying outliers. Box plots are another essential visualization in EDA. They summarize the distribution of a variable using quartiles and highlight outliers. The box shows the middle 50% of values while lines, whiskers extend to the rest. Any points outside the whiskers are potential anomalies. Box plots make it easy to compare distributions across groups. Scatter plots are perfect for exploring relationships between two variables. Each point represents a data pair and patterns can reveal correlations or clusters. If the points form a line, there may be a strong relationship. Scatter plots also help spot outliers that don't fit the general trend. Descriptive statistics are the backbone of EDA. Measures like mean, median, mode, range, and standard deviation help us summarize and compare datasets. These statistics give us a snapshot of what's typical and what's unusual, guiding our next steps in analysis. Central tendency refers to the center of a dataset, where most values cluster. The mean, median, and mode each give a different view of the center. Understanding central tendency helps us describe what's normal in our data and spot when something is off. Data spread tells us how much values vary. Measures like range, variance, and standard deviation show whether data points are tightly grouped or widely scattered. Understanding spread is key for detecting outliers and choosing the right modeling approach. Correlation analysis measures how two variables move together. A strong correlation means changes in one variable are linked to changes in another. EDA uses correlation coefficients and scatter plots to reveal these relationships, helping us decide which variables to include in models. Outliers are values that stand out from the rest. They can be errors, rare events, or important discoveries. EDA helps us identify outliers using visual tools like box plots and statistical tests. Once found, we decide whether to remove, correct, or keep them based on their impact. Missing data is common in real-world datasets. EDA helps us spot missing values and decide how to handle them. We might fill in gaps, remove incomplete rows, or use modeling techniques that can handle missing data. The right approach depends on the amount and pattern of missingness. Understanding data types is essential in EDA. Variables can be numerical, categorical, or even dates. Each type requires different summary statistics and visualizations. Recognizing data types early helps us choose the right tools for analysis and avoid mistakes. Univariate analysis looks at one variable at a time. We use histograms, box plots, and summary statistics to understand its distribution and spot outliers. This step gives us a clear picture of each variable before exploring relationships between them. Bivariate analysis explores the relationship between two variables. We use scatter plots, correlation coefficients, and cross-tabulations to see how variables interact. This helps us uncover patterns and dependencies that inform our modeling choices. Multivariate analysis looks at more than two variables at once. Techniques like pair plots and heat maps help us visualize complex relationships and interactions. This deeper analysis can reveal hidden patterns that single variable analysis might miss. Data cleaning is a key part of EDA. We fix errors, handle missing values, and standardize formats to ensure our analysis is accurate. Clean data leads to better insights and more reliable models, making this step essential before modeling. EDA often inspires feature engineering, creating new variables from existing data. By combining or transforming variables, we can highlight important patterns and improve model performance. EDA helps us spot opportunities for feature engineering. Transforming data can make patterns clearer and models more effective. Common transformations include scaling, normalizing, or taking logarithms of variables. EDA helps us decide which transformations are needed based on the data's distribution and relationships. Data entry errors can distort analysis. EDA helps us spot impossible values, duplicates, or inconsistencies. By cleaning these errors early, we ensure our results are trustworthy and our models are accurate. Understanding the distribution of variables is central to EDA. We look for normal, skewed, or bimodal distributions which affect modeling choices. Visual tools like histograms and box plots make it easy to see these patterns and decide on next steps. For data collected over time, EDA includes time series analysis. We look for trends, seasonality, and sudden changes. Line charts and moving averages help us visualize these patterns, guiding our approach to forecasting and modeling. Categorical variables require special attention in EDA. We use bar charts, frequency tables, and cross-tabulations to summarize and compare categories. This helps us spot dominant groups, rare categories, and potential issues with data coding. Numerical data analysis focuses on summarizing and visualizing numbers. We use measures like mean, median, and standard deviation, along with histograms and box plots, to understand the data's behavior and spot outliers. Visualizing relationships between variables is a key EDA task. Scatter plots, pair plots, and heat maps reveal how variables interact and whether there are clusters or trends worth exploring further. Multicollinearity occurs when variables are highly correlated with each other. EDA helps us detect this issue using correlation matrices and pair plots. Addressing multicollinearity is important for building reliable models. Sometimes, datasets have too many variables. EDA helps us reduce data by selecting the most relevant features or combining similar variables. This makes analysis simpler and models more efficient. Dimensionality reduction techniques like PCA help us summarize large datasets with many variables. EDA guides us in choosing and applying these techniques, making it easier to visualize and model complex data. EDA sometimes involves integrating data from multiple sources. We check for consistency, resolve conflicts, and ensure variables match up. Proper integration leads to richer analysis and more accurate models. EDA directly informs modeling decisions. By understanding data patterns, anomalies, and relationships, we can choose the right algorithms and avoid common pitfalls. EDA is the bridge between raw data and effective models. Even experienced analysts can make mistakes in EDA. Common errors include ignoring outliers, misinterpreting visualizations, or skipping data cleaning. Being thorough and systematic helps avoid these pitfalls and ensures reliable results. There are many tools that automate parts of EDA, generating summary statistics and visualizations quickly. While these tools save time, it's important to review results carefully and apply domain knowledge for the best insights. In practice, EDA is an iterative process. We explore, summarize, visualize, and clean data, then repeat as needed. Each round of EDA brings new insights and helps refine our analysis, making it a dynamic and creative part of data science. Let's look at a case study. Imagine you have sales data for a retail store. EDA would start by summarizing sales by day, detecting seasonal trends, and spotting days with unusually high or low sales. Visualizations like line charts and box plots help uncover these patterns and guide further analysis. In healthcare, EDA might involve summarizing patient ages, detecting outliers in lab results, and visualizing relationships between symptoms and outcomes. These steps help identify risk factors and improve patient care through data-driven insights. For financial data, EDA might focus on summarizing transactions, detecting fraudulent activity, and visualizing spending patterns. Spotting anomalies early can prevent losses and guide better financial decisions. In marketing, EDA helps summarize campaign results, detect unusual responses, and visualize customer segments. These insights help target the right audience and improve campaign effectiveness. With social media data, EDA involves summarizing likes, shares, and comments, detecting viral posts, and visualizing engagement trends. These steps help brands understand their audience and optimize content strategy. In manufacturing, EDA helps summarize production data, detect defects, and visualize process trends. Early detection of anomalies can improve quality control and reduce costs. For education data, EDA might involve summarizing test scores, detecting unusual performance, and visualizing trends across classes or schools. These insights help educators identify strengths and areas for improvement. Wrap up: exploratory data analysis is the foundation of any successful data project. By summarizing datasets, detecting patterns, and spotting anomalies, EDA helps us make informed modeling decisions. With the right tools and a systematic approach, EDA turns raw data into actionable insights. Now you're ready to apply EDA to your own data and unlock its full potential.